In this video, we're going to talk about the classification and isomers of amides. So we've done a lot with amines. Now we're going to focus in on amides, which remember is going to have the carbonyl group attached to the nitrogen, and then the nitrogen is going to be attached to two other groups and a lone pair. So for classifications of amines, we're always going to have the carbonyl carbon. So if the carbonyl carbon is there, and then both of the R groups are hydrogens, this is considered a primary amide. If we have our carbonyl attached to our nitrogen that has one carbon and one hydrogen, this is secondary. And then if all of the bonds to nitrogen are carbons, we have tertiary. So it goes with what we know. Some other labels are if we have only the carbonyl carbon and two hydrogens, this is called unsubstituted. Kind of the bare minimum to be considered an amide. Amide, amide, just if I bounce back and forth between those two, they're the same thing, two different ways of pronouncing that word. If I have one carbon group attached plus the carbonyl, this is monosubstituted. And then if I have two carbons with the carbonyl, it's disubstituted. So essentially that carbonyl is not counting because it always has to be there. What we're looking at are the other two groups and whether there's two hydrogen being unsubstituted, one carbon, one hydrogen, monosubstituted, two carbons, disubstituted. Another structural thing with amides are we can have cyclic amides, much like we had cyclic esters. So here is a cyclic amide or amide. We call these lactams. Remember we had the esters, those were lactones. The lactams are very commonly seen in penicillins. So again, you're seeing a lot of drug molecules that have these nitrogen-containing functional groups in them. For isomers of amides, we're going to again stick to just constitutional isomers. We're not going to consider skeletal or positional isomers here. We're just going to clump them all together. We also don't have functional group isomers this chapter. So amines and amides are not functional group isomers because we're adding in the double bond and the oxygen, so we can't go between the two. So if I have this, for example, as an amide and I want to draw an isomer, move a carbon. So I can either move a methyl group and branch something, or I can move that carbon and add it to the nitrogen. Back up here for a second. So I'm taking that carbon from the end of the longer chain and putting it on the nitrogen instead. So again, different structures, same formula, just our general classification of isomers. So let's look at these two structures. First question is, are these isomers of each other or not? So first thing we want to do always with isomers is count our atoms. So I have 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. So both of them are C5. I have a nitrogen in both and an oxygen in both. And then hydrogens, you can count them if you wish. The other thing you can do is look at the hydrogens that are drawn out. So I have two hydrogens shown on the nitrogen in both cases, and then I have a double bond in both cases. So if the number of multiple bonds and shown hydrogens, all the other hydrogens are also going to be the same. So we have 3, 5, 6, 9, 10, 11 hydrogens in both structures. So same formula. So now we need to ask ourselves, has something actually moved or are we just rotating? So I'm going to look at the longest chain that contains, oops, I'm erasing too much there. Longest chain that contains the carbonyl and the nitrogen. See if I can get rid of some details here and not everything. Nope. Start over here. Okay, so just redo the structure. So longest chain with the carbonyl and nitrogen, I have 2, 3, 4. If I look at the other structure, I have 2, 3, 4 carbons. So that carbonyl is what I'm calling number 4. The nitrogen, 2 hydrogens are attached to it. And then I also have this methyl group that's 1 carbon over from the carbonyl carbon. So these two structures really are the same. These are conformers. So conformers are always possible if it's just something rotating rather than actually moving. So if I wanted to draw an isomer of either of these structures, since the originals are the same, so I have 5 carbons total, so I'm going to put all 5 in a chain. I'm going to stick my carbonyl and nitrogen. I've already used all my carbons, so those just have to be hydrogens. So there would be an isomer of the original structures. So let's look at this structure we just drew and think of some ways we can label it. So is this a primary, secondary, or tertiary amide? So since we only are attached to the carbonyl, it is primary. We can also label it as unsubstituted, monosubstituted, or disubstituted. Since both of the groups that could change are just hydrogen, this would be unsubstituted.